Thank you, everybody. Thanks for coming to this talk. I hope you're having a great day so far and have energy left for this talk as well. I'm Pranav Prakash, one of the co-founders and VP Engineering at Quartic.ai. I've previously worked with SlideShare and LinkedIn, where I built search, recommendation, and content clustering engines, etc. I'm deeply passionate about AI, computer vision, and the potential of 3D printing. I'm also passionate about music and coffee, so happy to jump on a coffee conversation after the talk. In the next 40 minutes, you'll learn about a cool startup that is trying to make solving some real-life interesting use cases. We'll also see an example of downtime reduction of a critical asset from pharmaceutical and health sciences vertical. And I'll share a key insight that will enable us to solve these problems. We'll see the challenges in industrial stream processing, and I'll share some of the interesting Spark-related stuff that we have learned. So Quartic enables its customer transition into the next phase of industrial revolution. Often called Industry 4, this is characterized by autonomous factories working together with raw materials, manufacturing, logistics, and sale to improve the entire industrial value chain. Before we dive into Industry 4, we need to understand where Industry 4 is coming from and what it tries to cater to. So Industry 4 is coming from Industry 3, which started somewhere around 1960s and 70s. With the advancement of microprocessors and computers, people automated a lot of manufacturing and industrial jobs. The data from all these systems was collected and presented to a human operator to make decisions. Now, these decisions could be real-time, for example, increasing the RPM of a motor to account for an increased workload or an irregularity, or it could be a longer-term decision like scheduling downtime of a critical asset. Now, industrial equipments typically generate large amount of data. So an equipment that is used to extract protein from egg generates typically about 5 billion data points per day. Now, this is captured through 2,000 different sensors polling at 20 milliseconds granularity. The aim of Industry 4 is to harness this data to enable data-driven decisions for efficient production, optimal usage of the raw materials and resources, for reducing the downtime, and for reducing any safety hazard that could happen in the industrial side. So let's look at what it takes to build a platform for Industry 4. In order to get the entire context for Industry 4, which is smart manufacturing, one needs to capture data from many kind of different data sources. These could be data from sensors, which are about the details of asset and the process that is happening. This could be data from manufacturing execution systems that contains the broader context of the process that is happening. It could also be data from your ERP systems, which is where the business data is stored, such as what to produce, in what quantity, where to ship, etc. And then it could be data from various other ecosystem platforms. For example, someone could use landing.ai's data about quality and loop it back into the manufacturing data to ensure that the quality feedback is happening during your manufacturing itself. So Quartic's platform is essentially made up of two major components. The first component is called Illuminator, which is the data engine and responsible for collecting data from all these diverse data sources. So some of these data are time series data, which is coming from sensors. And then there are other data which is mostly discrete in nature, coming from ERP systems and manufacturing execution systems. Once all this data has landed into the platform, the next major component of the platform, called Exponents, is the data engine. It's the intelligence engine at Quartic. So at Quartic, we believe that the true potential of any AI application comes when you empower the subject matter expert with AI. Like a person who has worked with these machines for 10 years, 5 years, knows much better than any data scientist. So in our platform, we have different workflows wherein an operator or somebody in the plant can use the platform and create machine learning models and applications and then deploy it on the platform itself, which is what exactly Exponents does. It is responsible for processing these incoming data, performing analytical machine learning processing, creating insights out of this data, and recommending these insights to the customers. So We started by building solutions for pharmaceutical manufacturing and created a DIY platform because, like I said, the true power of AI application is when AI is combined together with the subject matter expert. So these are some of the use cases that we have done, and I'll dive deeper into the first use case, which is the increasing the uptime of a sterilization autoclave by about a week. So this is what an autoclave looks like. It's a very complex asset that is mostly used in life sciences and pharmaceutical vertical. Think of autoclave as an industrial pressure cooker. There's very high temperature and pressure inside it, which essentially kills all your germs, bacteria, etc., to make sure that the product is sterilized before it reaches the consumer. Now this is a very critical asset because any product that is manufactured in any of the earlier pipelines must go through an array of autoclaves for it to be sterilized. So a downtime in one of these autoclaves could result in a downtime of the entire production pipeline altogether. Now this asset runs 24/7 and it runs into various different modes. Now these different modes, think of them as different modes in your washing machine, for example. Like there is a fast run mode and there is a deep cleaning mode, but all these modes essentially have the same phases, which is your water gets filled into the washing machine, then there's a spinning of the wheel, and then it goes to dryer, etc. So similarly, autoclave also works in different modes, and these modes have different phases. Now, what it takes to build a system to create, to monitor this and to enable the required uptime for this. Now, if I ask a plant operator and I tell that I need to define the downtime of this autoclave, that itself doesn't make any sense to it. This equipment is made up of many different critical components, and a failure in any of these components could lead to a failure of the entire system altogether. So one starts by first identifying the critical components in these industrial assets or equipments, and then doing something about it. What needs to be done, that we'll see later. So when we started working with industries, we realized that there is two different kinds of data that is essentially required to create the entire context. The first kind of data is called process data. Process data is the real-time value of a process that you are trying to monitor or control. For example, in your microwave, your temperature is the process data because that is what the user wants to control for. Then there's condition data. Condition data tells us about the condition of the equipment while it is trying to maintain a certain value for your process variables. In this case of microwave, the vibration of microwave will be your condition data. Now, what we have realized is that in most industries, which have been running for like 50 or 30 years or even 10 years, people typically ignore the condition data of the equipment. They store the process data because that is required by FDA and other policies to keep it intact, but typically people ignore the condition data of the equipment. Now, condition data, unless we merge condition and process data, we can't really create the exact context about an equipment's health. The idea is that if your microwave is vibrating more in order to keep the same temperature, that could be a sign of a degradation of the microwave. That could lead to eventual breakdown, or it could lead to higher energy consumption. So the key insight here is combining process data and making sure that we have the condition data being monitored and combined with the process data to create the right kind of context. Now, when we talk about determining the uptime and downtime of an asset, it's the first step is to kind of figure out the baseline for that equipment, and then be able to measure the deviations on top of it. So in case of this autoclave, we have about 150 different critical components. So we need to create baseline for all those 150 components and then be able to measure the deviations. Now this directly translates into about 150 machine learning models from anomaly detection that are very good at creating your baseline and finding out anomalies and irregularities out of it. So what this does is that it helps the operator in real time to identify if something is going wrong, and then there are other ways in which we present the influencing factors for this anomaly so that the operator can understand what is causing this deviation from the behavior. Now, once this baseline and the deviations are established and measured, the next step is to be able to forecast some of these variables into the future. Now, typically, operators would want to forecast such values which can be controlled. There's no point of forecasting a value that the operator can't really control. So that takes us to the next step, which is forecasting, which is using prediction models to forecast the value of a particular variable after a certain point of time. The idea is that if the operator knows that, and once we have these forecast models being done, then we can use the anomaly detection models on top of the forecasted value to predict if in the future there is going to be an anomaly or not. And if the operator has this context, then the operator can do something about it. The operator can change the way this equipment is being operated, or they can plan downtime for this, or they can figure out a way in which this equipment needs to be operated so that the downtime gets reduced. Now, typically in industries, the incidents don't happen in isolation. There is usually something that breaks down which leads to breakdown of some other thing, and there's some other thing breaks down, and then eventually your entire equipment breaks down. So being able to identify these early signs of anomalies and being able to classify them correctly into a proper failure mode and effect analysis helps the operators identify a downtime that could happen in the future. And for a downtime that has already happened, or an incident that has already happened, it helps identify the root cause of that particular downtime. So what we see is that using these very common approaches of machine learning, anomaly detection, prediction, and classification, one can build a system which essentially helps the operator understand their equipment in much better manner and helps them operate it in a much better manner. Now, typically, industrial AI or industrial IoT in general is an emerging field, and most of the customers are in the early adopters phase. Some of them are moving from early adopters to early majority, but what is common across all these customers is that they want a transparent white box AI, wherein they can understand what is happening, why it is happening, and can use their own logic and intuition, which they have gathered over years, to ensure that it is correct. So most of the AI platforms are, including ours, is in advisory mode, wherein the platform recommends certain action to the user with a confidence score, and then depending on all these different kind of recommendations and their confidence scores, as well as the influencing factors, etc., the operator takes certain decisions. Now, these decisions are captured by the platform and then used as a feedback to improve the models and the learnings of the model. So let's look at what a typical data flow looks like in this scenario. So what we have is two different assets, asset 1 and 2. These are all equipments. And each of these equipments are connected to 3 different sensors. 1, 2, 3 goes to the first equipment, and 4, 5, 6 goes to the second equipment. Now, these sensors are connected to PLCs, and these PLCs are in turn connected to SCADA systems, which actually performs the supervisory control and is responsible for capturing data from all these sensors. Now, because of the way industries and these equipments evolve, there could be a scenario wherein a data from one equipment lands up into 2 different SCADA systems. Like in this case, the sensors 3 and 4 are connected to the same PLC, which sends its data to SCADA 1 system. Now, once these SCADA systems have this data, and then there is Quartic connector that captures this data from these SCADA systems, creates a corresponding message that contains the information, the real-time value of those sensors, and passes it on to a Kafka telemetry topic into different partitions. Now, what we see here is that in this kind of case is very common. So you will have data from the same equipment landing up into different Kafka partitions. Now, most of the processing is done in the context of an asset. So in this kind of a processing, one would always typically want to repartition the input stream so that you have your data from the same equipment landing in the same partition, so that processing could be done. So let's look at what are some of the design parameters of a system like this. The first and most important is the speed of data and the volume of data. So industrial equipments typically have a wide range of the speed of data. Some of them could capture data at as high speed as 10 milliseconds, while some others could be doing at about 2 hours. Combine this with the volume of data. So every equipment typically needs a couple of hundreds to thousands of sensors, and an enterprise has typically tens of thousands of different equipments across various geography. So what this means is that, going to the previous diagram, so when you are trying to put data from different sources into different partitions into Kafka topic, what one wants to do is to put in data which have similar speed into a same partition. Because if it's not done, then what could end up happening is you have a 10 millisecond data and a 2-hour speed data landing into the same partition, and if you are processing both of these data together, you could end up in a situation wherein one of the data is being favored while the other is being not. So one typically wants to put data from similar data speed into the same partitions. So, and then there are different types of data types, string, numeric, Boolean, array, etc. But for the purpose of machine learning and doing equipment reliability, we typically talk about time series data itself. The other key important aspect is the nature of deployment. So Quartic Stack was born in the cloud. But working with the customers, we realized that about 70 to 80% of the customers are not interested in a cloud platform. And there could be multiple reasons for it. Lack of internet, for example. You can't really expect a high-speed internet at an offshore oil mining site. And then there are certain other customers who have policies around transferring of data outside of their site itself. So most of the solutions need to be on-premise. And this is where some of the great cloud-only solutions like the Databricks platform doesn't really apply to us. Some of these deployments really have a very high uptime and low response time. Cloud is typically 20% of the entire business. So the solutions that we build are deployment agnostic, which are primarily focused on the edge, but also caters to the cloud as well. Now, now looking at some of the use cases that one needs to do. So like I said, the platform is mostly meant for industrial users who don't really know data science or computer science. But there is a workflow through which they can actually go ahead and create a model, train it, and deploy that model on live streaming data without even understanding what is happening in between, under the hoods. And then these models, and then there are thousands of models that needs to be deployed. And typically, along with the output from these models and the raw sensor data, there are a couple of more things that a user needs to do. So some of them could be creating new insights and metrics based on your raw data. And then there could be business rules that needs to be applied on this metrics and insights, which is where your complex event processing comes into picture. And then there are, of course, various other kind of statistical and analytical processing to figure out some very basic insights. Now, all this processing is pretty much near real time in nature, which is where Spark streaming actually comes into picture. So let's look at some of the challenges that we have in this case. So especially with related to machine learning, there are a couple of challenges, and most of them are because the nature of the data is very heterogeneous. You could have data from different streams, different assets, and all these data have different sensors, etc. They all land up together, and one needs to process all of this to create the right kind of insights or metrics. There's also a late data arrival and model deployment on heterogeneous data streams that we will dive deeper into. So in this case, we have the sensors A, B, C, and D. They all four belong to the same asset or equipment, but then they have different granularity. So while sensor A and sensor B are polling at 1 second interval, we have sensor C and D which are polling at 5 second interval. So depending on if the kind of model that we are building, if the target is sensor A, one would typically want to have the values from, so if the target is sensor A, and in this case, let's assume that the features are sensor B and sensor C. So in this case, while creating, while processing the data from these sensors for a machine learning purpose, one would want to have data from all the influencing, from all the features to be present at all the times. So this is where some very common techniques like approximation and aggregation could be used to fill the data where it is not available. So in this case, if we are doing with sensor A and we are trying to predict a value at 12:03 02, then in that case, one would want to forward fill the data from sensor C by using some of these techniques to make sure that we have the data from all these feature sensors being present while the compute is happening. And no discussion about stream processing is complete without late data arrival. So how many of you have seen this diagram before or heard about watermarking with Spark? Okay, so mixed crowd. So I'll explain this a bit. So this diagram is actually taken from the official Spark documentation, and it talks about a concept called watermarking. So what happens is that in structured streaming, the Spark engine can maintain intermediate states of windows over a long period of time. What it does is that it allows a data that arrives late to update the values of the intermediate states. But then in a streaming application that runs for weeks and days, there needs to be an upper bound of how much intermediate data can be stored. And this is where in Spark 2.1, the concept of watermarking was introduced. So one can create watermark by, so watermarking lets the engine automatically track the current event time based on the data from the message and then updates the old state accordingly. So one can define watermark by query and specifying the event time column and the threshold after which the data is not allowed. So the idea is that if your data is landing before your threshold, it can still be used during the computation, while if it lands after the threshold, that data is ignored. So this typically works for homogeneous stream of data wherein there is one kind of processing being involved and the data is also of one nature. Now in industrial case, the data that we are talking about is pretty much heterogeneous. So what we have done is evolved the notion of watermark to account for this kind of a scenario. So, yep, this is clear. So what we are seeing here is the idea of watermark which has been extended. In this case, we are talking about two different equipments, asset 1, asset 2, and both of these equipments are generating data at different intervals. So while asset 1 is generating it at a 1 minute interval and asset 2 is generating it at 2 minutes of interval. And imagine a scenario wherein there are two machine learning models deployed, model A and model B. While model A just depends on your data from asset 1, model B depends on your data from asset 1 and 2 both. So in this case, and the Spark batch interval is 2 minutes. So we see that some of the data from asset 1 is coming right on time, while some of the other data is arriving late. So what happens is that when the first Spark batch happens at 10:02, then we have the required data from asset 1 being available for the model processing. So all of that is sent for processing. Similarly, for model B also in this case at 10:02, we have all the data being available. So that is also sent out for processing. Now what happens is when we are when the next batch interval happens at 10:04, for model A, it really doesn't matter because model A is independent of any other values from other assets. But while for model B, we just have one data arriving here, which is the one at 10:04, and the other data is arriving late. So that will be processed in the next batch interval. So in the next batch interval at 10:06, we have again all the data being available, and then the watermark time is complete, so that data is sent out for processing. So this is a very key insight here because typically in the kind of applications that we work, one always needs to combine, not always, but in a lot of scenarios, one needs to combine data from multiple different sources at different frequencies to perform these computations. Now in this example, we are talking about two different equipments, but one can very well relate to this wherein the equipment is same, but your sensors are different. So you could have data from one of the sensors arriving early, you could have data from one of the other sensors arriving late. And the same notion of watermarking could be used in all these kind of different cases. And so this is the sum up of all the watermarking and aggregation being shown here. So on the left, we have the same example of asset 1 and asset 2. And once we have the data available, because in this case, so the way this watermarking happens is that you typically choose your watermark time as the maximum time of, as the highest common factor of the maximum granularity at which your data is being expected. So in this case, the watermark time for model B goes every 2 minutes. You would want, because that is the maximum granularity at which data from asset 2 arrives. While the watermark interval for model A will be just 1 minute, because that's all data that we have there. So in this case, when the data from all these different assets land up together and we have a common watermark time available, so both of these data are aggregated. In this case, we have averaged it out, and this data is then combined with the data coming from different sensors to create one watermark row that has all the required sensors data available, which is then sent to machine learning engine for processing. Now, what about model deployment? So in our case, it's the Cortic platform through which the users create these models and through which they deploy these models. And we are talking about thousands and thousands of models. So what we have done is we have created a web service which actually hosts and serves these models. And then there's a Spark streaming application which takes data from multiple different Kafka topics. These could be your topic from raw sensor data. These could be your topic from the metrics that have been created and various other sources. All of them are brought in together. And the standard pre-computation about watermarking, checkpointing is happening in this Spark streaming job itself. And once the required data is available, then it makes an HTTP request to the cluster serving these models, and then the response is obtained, which is then forwarded back to the machine learning output topic altogether. Now, this diagram may look familiar to some of you who have been working with MLflow for quite some time. And interestingly, when we started, MLflow was just releasing up, and we kind of chose to go with this approach. So in industrial scenario, there is also a case wherein you have a flash flood of data happening. And this typically happens because let me go back to the other slide. Yes, so in this case, so these Cortic connectors, these are on different physical machines altogether. And this data is sent to a Kafka topic. So what could happen is that the network connection between these connectors and the Kafka broker is lost, in which case the connectors still cache all the data locally. And once the network resumes, they send all the data that has been cached into the Kafka topic, which could result in a situation wherein there is a high spike of data. It could be for a short amount of time or for a longer amount of time. Now, typically, in order to handle data spikes and a flash flood of data, there is a great config in Spark Kafka connector, which is your back pressure. So, and this back pressure can essentially allows the ingestion rate, allows the engine to automatically define the ingestion rate of data, so that your each Spark batch processes a finite number of data points, and it doesn't eventually leads up to OOM or any other crashes with the application. So the current controller that back pressure has is a PID controller, which works great for most of the cases. But if someone wants, they can actually create a different kind of controller as well. Now, this brings us to the next topic of complex event processing, which are, there are two different ways in which we can do this. So one is creating insights and metrics that could, so what happens is typically there are thousands and thousands of sensor data arriving, and on all this data, there are hundreds of insights and metrics that people write. So in order to optimize for the compute resources, because your hardware is limited on the edge, one needs to make sure that none of the computation is happening duplicate, which is where the directed acyclic graph approach comes into picture. You could create a graph like this and process all the metrics without without doing any redundant computation. So for this, we have used PySpark, and there's a great library, Yahoo GraphKit, that enables us to achieve this. And the reason to choose PySpark with a Python-based implementation is because in our platform, the users typically create these metrics and insight over a Python interface itself. Now, for the business rules, we have an engine called Rules that works great with Scala Spark, and it can be deployed to ensure that all the business rules are computed properly and all the events are generated as they should be. So that sums up my presentation. We have seen that industrial IoT is different, primarily because of the nature of data stream. It's heterogeneous, and there's just a lot of different variety of data that needs to be processed together. The key insight is that the context in case of smart manufacturing or in case of industrial equipment and reliability comes totally with the process data and condition data. Condition data is really, really important. And we have seen some of the techniques for processing heterogeneous data stream. So that was all. If you find this interesting, we are hiring. So drop us an email, and I'll take questions now.
Hi, very good presentation. My question was with regards to what you mentioned earlier in your talk about transparent models and white box models being preferred in this case. So what type of models are you using specifically to provide those insights to the end users? So that question number one. And related question again on the model is that once your models are deployed, models generally typically in these kind of environments start to age. So when is it, and how do you decide to upgrade them or remove them or modify them?
Great question. So in the kind of models that we use are XGBoost and GMM. So some not like deep learning models. We use the kind of models that can actually help us derive insight about what factors influence the outcome by how much, because we need to present an influencing score to the operator as well. And coming to the second question about model degradation, that is something that is very that happens with the platform itself, because there is a model monitoring process through which the users are notified if there is a gradual degradation in the model itself. Because typically in these scenarios, there is one thing about the degradation of model, and then there is a degradation of the actual equipment altogether. So your baseline keeps on shifting after a certain usage altogether. So there needs to be a model monitoring case which alerts the user that, hey, now it's time to retrain your model, and the users then use our workflow to provide new training data and retrain the model. Does that answer your question?
Which libraries do you use to get insights from the models to the business users?
So we have our own custom implementation of models. Like I said, like these are XGBoost and some fairly simple models, nothing GNN or some advanced deep learning models. So we have our own framework that extracts insight from these models, and then it is presented to the user.
Hi, thanks for the presentation. I have a two-part question. The first one is regarding the deviation detection. Generally for process and condition monitoring, typically they will have alarm and trip settings. So a high temperature alarm, for example. So when it hits the set point, then it will trigger an alarm. Hits the trip, then it will trip the system. So how does that differ to the deviation detection that you are doing? Also, a second part is about typically in the industry, what we face is unbalanced data. So we have more normal condition than upset conditions, and how do you address that? Thanks.
Right. So, sorry, could you come again with the first part of the question?
The first part is about the deviation versus like
Right.
alarms and trip settings.
Right. So typically those alarms and trip settings are rule-based conditions. So you could put an alarm like if it goes beyond 100 degrees centigrade, trigger an alarm for this. Versus, and that is like the last resort. Like if that alarm triggers, some operator needs to take an immediate action on this. The deviations will start to affect much before than that. So if your normal operating range is, let's say, 80 to 90 degrees centigrade, and the alarm is set at 100 degrees centigrade. So as soon as a trend starts to build up wherein your temperature is going beyond a certain operating range, that is that is observed and presented to the user that this deviation has already started, and one wouldn't typically want to wait until it reaches that rule condition. So that's the basic difference. It's like the same difference that we have with a rule-based system versus a machine learning model. And sorry, the second part of the question?
It's unbalanced data.
Yes, is the unbalanced data. So that is that happens very commonly because typically in industries people change equipments and sensors. So you don't have a lot of downtime cases. So in that case, our workflow has a method wherein the user can simulate anomalies. They can look at the actual data of working conditions, and then they can simulate certain anomalies, which is used to train the model itself.
Thanks.
Hello, good talk. I have a question because you're doing lots of things in the edge. Do you have a methodology to transfer, let's say a customer has several factories and the data is not allowed to cross the border of the countries, to get the knowledge from one factory to the other factory where they have the same equipment? Yes,
so that is something that we are also trying to figure out what's the best way, because these data can't really be sent over to cloud. So typically in certain enterprises wherein there is intra-connectivity between different geographies, we have something called as a transfer learning. So you can you can learn from all your equipments at site 1, and then you can transfer the same information or learning to site 2 as well. So you don't really need to wait for an incident to happen at site 2. So your entire enterprise becomes smarter eventually.
Okay, thanks.
Thank you. Any other questions?
Great talk, thanks. At the start you mentioned the correlations between events. How do you keep track of that? So if something happens more upstream and that actually breaks something downstream, do you keep track of some kind of graph, or do you analyze what the factory looks like or what the equipment looks like and how it hangs together? And right. How do you filter for the false correlations?
Right, so typically what happens is these enterprises and industries have been for so long, they have something called as a failure mode and effect analysis that can be used to identify these individual symptoms and link it to a bigger downtime that could happen at a later point of time. So the idea is that this information which already exists could be brought into an AI platform, and your platform could use this information along with your classification models to predict where this is eventually going to lead.
That will be rule-based then in your AI model?
Sorry?
That will be rule-based?
So no, that won't really be a rule-based. That is a classification model, right? So some of the things are not really rule-based, but there are failure modes. So your equipment could fail because X has happened, and then Y has happened, and Z has happened. So just and this could be deviation. So after X and Y, it's not necessary there could be a Z. There could be a path that takes to P as well, right? So being able to classify these kind of incidents helps identify the future downtime or the root cause of an incident.
Okay, but that would be the training bit, as in you.
Yes.
You learn that yourself.
Yes.
Yeah. Okay. Thanks.
Time for one more question.
Hi. What tools are you using for managing the Spark clusters, Kafka, and other technologies that you are using?
Right, so all of it is Dockerized and orchestrated by Kubernetes. That's all the tools that we have essentially, because in case of edge deployments, most of the most interesting tools are available for cloud only. So in case of edge, you are limited to some of the existing tools for DevOps related stuff, which is where Kubernetes takes care of the entire orchestration, and then there are Docker-based deployments of Kafka and Spark and other systems. Does that answer?
All right, that's a wrap. Well, thank you, everyone.
Thank you.